So now to the keynote. So sorry, I copied the slide. So the keynote, let's just switch back. All right, now it stays. So the keynote is by Cora and Paul-Emmanuel. Here you see Cora. At the third slide you will see Paul-Emmanuel. And the title is Secure Connected Multimodal Mobility and Using Vehicles as Sensors. And let me briefly introduce the two speakers. They are both with AIRBUS, and Cora Perner has been with AIRBUS for over 6 years and leads several research projects. She has completed her PhD in computer science from Technical University of Munich, and she has a degree in Aerospace Vehicle Design from Cranfield University in the UK. Her research focuses on the intersection between safety and security of unoccupied and autonomous aerial vehicles, as well as the safe integration of new technologies and methods. She has been working on several national and European projects in the past years. In addition, she has published 7 papers at distinguished international conferences. And we have Paul-Emmanuel. Well, he's passionate about innovation, cybersecurity, IoT, and identity management. He is an expert in IoT system security within AIRBUS. During the last 10 years, he acquired a strong technical background in cybersecurity and IoT by contributing to national and European programs in various positions within AIRBUS cybersecurity, which are from integrator to team leader of IoT and identity and access management engineering team. Along his career, Paul-Emmanuel also applied several patents and participated to several conferences. He is now leading the innovation and R&D team in France. Okay, so then we can watch the trailer.
The talk will start with a description of some way to secure the connected cars environment by enabling hardening of communications and cybersecurity monitoring of the communication exchanges through the bus.
It will continue with a discussion on communication for mobile vehicles, so in both cars and unoccupied area systems. And in the end, there will be a bit of an excursion on autonomy and the impact that autonomy, particularly for aircraft, has on security properties.
Lars, could you please keep me up there? Okay, and so as usual, there is the Slido, and please ask your questions there. If you're in the audience, you can also, and should also ask your questions directly here. And as always, the speakers will be very happy about questions. And yeah, so this was the last slide I wanted to show. So now you can switch, and we can welcome Paul-Emmanuel and Cora with a warm applause.
Okay, can you hear me?
Yes, perfectly.
Perfect. So first of all, thanks a lot for this opportunity to give this speech. So on the menu today, we have two main topics. As the first topic, I will present some challenges around cybersecurity and data privacy in the ecosystem of the connected vehicles. On the second point, Cora, I will leave the floor to Cora to tackle the challenges around collaborative and autonomous aircraft systems. So Cora, could you go through the slides? Thanks. Okay, so now if we go to the next slides, let's go through the challenge around connected cars. So let's talk about a connected car. These cars offers quite services. This could be, for example, a third-party application for the traffic management, this kind of stuffs. There is also communication with the overall infrastructure, such as the Red Cross. There is the management of some personal data, GPS position, all this kind of stuff. So what quite a lot of information, but is also discussing with many other components in its ecosystems. Once we have told that, what we can see is also some threats on these ecosystems. This could be, let's say, some spamming from the infrastructure to the car from, let's say, hackers. There could be some ODB attack through for example, the entertainment systems. That was done a few years ago now. There could be some malware attack on the entertainment systems to let's say take the control over the car, and all these threats are let's say a short summary of what can happen to the car. Using these threats, some hacker can have access to some personal data, but also can take the control over the car, get more information on the speeds, control some critical elements of the car, such as the brakes, all this kind of stuff. Now, if we go to the next slides, let's talk about a short history around let's say the car attacks. The most common, what we've seen in the past is that the car manufacturer have been, let's say, have suffered quite a lot of security breach. It mainly started by what we call the radio amplification attacks that was used in order to, let's say, to use the key to take the control over the radio messages sent by the key of the car in order to unlock and install the car. So that was quite common in the past as an attack. And now that we have more complex and more connected vehicles, what we have seen since few years now is the multiplication of attack on the entertainment systems. For example, we have a few years ago Jeep, who was quite well known example of attack of the entertainment system in order to take the control over the car. There was also some example around Tesla, which was a victim from malicious attack also on the entertainment systems and from let's say website upgrade in order to take the control of braking system. There was also an example of attack between the communication of the vehicle and the cloud with the GoGet customer, which is a sharing app in Australia, which was compromised in order to gather some personal information on their customers. So this show more the privacy breach, and the previous one were more related to safety impact of the cybersecurity attacks. So now if we go to the next slides, we will see what are the main challenges. So in the picture, you can see, let's say, an overview of the security architecture we can set up to let's say, to fight those threats. We will focus on 5 areas of interest. So the first one is the communication between the vehicle to the infrastructure. The second one will be the communication between the vehicle to the other vehicle. Typical use case is to know the distance between vehicle and understand the number of vehicle in the area, this kind of use cases. The third area of interest is the communication between the vehicle to the cloud. So typically, this is a communication that is used for some onboard, on-vehicle services, such as knowing the traffic jam area, checking the GPS information, this kind of stuff. In the fourth, we have the in-vehicle communication between different component entertainment systems, onboard unit, etc. And finally, we have what we call the other area of interest, which is more on the cloud part, meaning that by corrupting the cloud part, you can also take the control over the car. So this is also from the cybersecurity point of view and privacy point of view, a key point of interest. So regarding that, we see three main challenges related to this ecosystem. The first one is to ensure the communication security, guarantee that the confidentiality and the authenticity of exchanges is guaranteed and cannot be hacked. Meaning that we cannot, let's say, spoof the identity of a vehicle or this kind of attacks. The second challenge is to ensure the cybersecurity monitoring. We know that protection mechanisms could bring, let's say, a certain cybersecurity level, but it's also very important to be able to monitor the behavior of the vehicle and the ecosystems. So that's why the cybersecurity monitoring of the whole ecosystem is also a key point. The third point is also really important. It is related to the data privacy. When we talk about vehicle, we are dealing, as I said before, with a lot of privacy data and personal data. So that means that we have to ensure that the privacy is respected, especially taking into account the European regulation on that with the GDPR, for example, which are key regulations to ensure the data privacy and ensure the citizen privacy. So now if we go to the next slides, we will see an example on how to tackle the first challenge. So that there is two main functions, let's say, to tackle the first challenge. The first one is to ensure that an entity, a vehicle or an infrastructure, which is communicating over the system is allowed to do so. So for that, there is some standards that were published by the ETSI standardization body. There was some technical specification that were published for that, specifically relying to the, let's say, the automotive area, but also can be extended to other kind of vehicle in the large sense of the word. And this system can typically exchange some secret information between vehicle and the other entities in order to encrypt and authenticate each information that is going through the communication channel. The second point is the privacy. Because when we authenticate, we most of the time send some privacy-related information. But typically, we don't want to be able to track that my personal vehicle have go through a specific path. So that's why it's also very important to take into account the pseudonymization of the authentication of the vehicle in order to ensure that the privacy will be respected and that for example, what we call the roadside unit or the equipment along the road won't be able to track the communication of the car with at least with personal information. So that's for the first challenge. Now, if we go to the next slide, we will go through the cybersecurity monitoring. So, as I said, it's a key challenge because on the one hand, we have to monitor the behavior of the vehicle, But on the other hand, it's really a technical challenge also, because we have a lot of vehicle to monitor. What we want to monitor is on the first part, the vehicle itself, the behavior of the different components within the vehicle, but also the behavior of the system and the whole system itself. So that's why we need to monitor, meaning that we want to assess and report any kind of vulnerabilities, monitoring, let's say, abnormal behavior, and this kind of stuff, in order to be able to react. For example, if we detect any cybersecurity related alerts. So that is for the second challenge. And now if we go to the next slide, we will speak a little bit about the third challenge, about privacy. Privacy is not an easy challenge. Indeed, as I explained in the let's say the access control challenge, there is this issue of ensuring the anonymization of the car communication to be sure that we are not leaking any private information to third-party equipment. But there is also a challenge on the cybersecurity part, because when we are monitoring information, most of the time we are collecting potentially some personal information, car identifier, and this kind of stuff, that are key in order to correlate different events within the whole system to detect abnormal behavior. So that's why we think that it is very important to ensure that there is an anonymization of this kind of information before sending any alerts or cybersecurity events to a central system. That's why we also have worked within AIRBUS on these topics on anonymization with some external partners also, to ensure that the cybersecurity ecosystems that we set up to secure the connected car environment is also able to respect this anonymization issue. So that's if we go now to the next slide, just to highlight some key messages of this first part of the presentation. So the connected car is indeed a world of threats. I don't want to be too pessimistic, but that needs to be taken into account. It's also a world of opportunities, because this will also bring more and more additional services on the connected car, and it's a key challenges also for the path to the autonomy of the car. The second point is that there is standards and solutions that exist in order to bring bring security to this environment and to guarantee the safety of those connected cars. And finally, the last point I would like to highlight is that cybersecurity protection measures have to guarantee the privacy. Meaning here that it's very nice to bring privacy measures to secure the let's say the leak of potential privacy data, but it's very important also to take into account that the cybersecurity protection measures could have impact on the privacy, and that's why we need to take that into account when we build those protection in order to guarantee the whole system privacy. So that's okay for the first part. I will leave the floor to Cora, and afterward we could keep some time for the questions. Cora, the floor is yours.
Thank you, Paul-Emmanuel. Can I just get a short thumbs up if you can hear me? Perfect, thank you. So I'm now going to talk about security challenges for collaborative autonomous aircraft systems. Now, what I'm going to talk about specifically is I'm giving a brief introduction into autonomy. Those of you who have a background in autonomous cars will find some similarities, and it would be quite familiar to you. Then I'm going to talk about what challenges that brings us, especially in the context of flying vehicles, as we increase autonomy. And I'm going, yeah. So as far as an introduction to autonomy goes, there are some challenges if we want to use more flying vehicles in various contexts. So on the first hand, from a safety perspective, there's been a significant increase in reported near misses. So when a UAV of some sorts came into contact with a piloted aircraft, with a passenger aircraft, this is the data just for the UK alone. So in 2018, you can see that the growth is massive briefly. And what's more is most systems that we use in air traffic management, so which control how vehicles can stay safely separate from one another, are outdated. So they use radar, they use means that can't really detect UAVs, especially not if they're malicious. And moreover, there are emerging cyber threats. As vehicles become more connected, they are also more vulnerable to cyber attacks. On the other hand, they can also be very, very useful. So they can be used for sensing, for example, for infrastructure inspection or surveys, where it's just too dangerous for humans to do the inspection themselves, or where it can be much faster, for example, if you fly over a power line. The next one is for transportation. So both for people and goods. So for example, you can imagine that your favorite packet delivery provider uses UAVs to transport your pizza or your newest online shopping packet to you directly without having to use cars, which parking and etc. is a challenge. And they can also be used for emergencies. So for example, for ambulances when you're in very congested cities, you don't have to go through traffic jams, and also for firefighting, both for inspection and also for mitigating them. So let me start on terminology. So drones are male bees. I know it's used commonly. It's also used in publications you will find, but it's not terribly helpful, and I'm going to explain to you why. So when you use a term like drone, you can't really tell, is it automated, is it remotely piloted, is there a human loop or not? So what you can use alternatively and interchangeably is either the term unoccupied or uncrewed aerial vehicle. Both of these terms don't really give you a hint of whether it's piloted or whether there's a human in the loop or not. Generally, there isn't. But the terms, usually you use the term unoccupied aerial vehicle for something you can buy as a toy for your children or yourself, of course, and uncrewed air system for professional applications. The terms can be more less used interchangeably. The next point, which actually tells you it's how it's piloted, is the term of remotely piloted aerial system. So that really tells you there is a human on the ground that pilots the aircraft remotely. And the third term, of course, is an autonomous aerial vehicle. As the term suggests, it's autonomous. There may still be a human sort of supervising it or taking over if some system fails, but those are the general distinctions. So let's now go through the autonomy levels specifically for UAVs. As I said in the beginning, if you're if you have an automotive background, these levels won't be terribly surprising and will be very familiar. So at the first level, obviously there's no automation. The control is 100% manual, and obstacle avoidance is automatic obstacle avoidance is non-existing. Then for the first level of low automation, the pilot remains in control, but the UAV has control of at least one vital function. So that could, for example, mean it could control its engine setting, for example, and prevents its not overspeeding. The second level is where the pilot remains responsible for safe operation, but the UAV can take over heading and altitude under certain conditions. So, for example, there is a return to home function. Then the third step is conditional automation. So that acts as a fallback system. You typically have the route pre-programmed, and the UAV can perform all functions given certain conditions. So, for example, wind speed doesn't exceed a certain quality. The next step, level 4, is pilot is out of the loop. However, the UAV has backup systems, so if one fails, the platform will still be operational. And the final steps is obviously full automation, where the UAVs can plan their flights and typically also involves some degree of AI to react to things that weren't part of the pipeline, so for example, to gusts of wind, and the UAV can also learn to a certain degree. So what does that mean in terms of cybersecurity? So at the very low levels, you can obviously have or be interested from cybersecurity in the command and control link. So you can perform, for example, eavesdropping, information injection, you can perform a denial of service, or you can spoof the command and control link. So that means in practice you can take over the control of the vehicle. Moreover, at these low levels of automation, generally they're also the cheaper products. The communication links are not usually encrypted. So if you go to a toy store and buy 200, 300 euro UAV there, typically you probably won't get an encryption communication link. Or if you have one, it uses a proprietary encryption where you don't exactly know what's behind, and there haven't been really excessive studies done on how secure it is or not. And you can, of course, also take over the UAV with cyber attacks. On the next level, you can, for example, intentionally deactivate support systems. So, for example, hard-coded no-fly zones. So where the vehicle by the manufacturer is prevented to fly over certain areas where it's not permitted, for example, in the airports. But the vehicle won't immediately crash if there is a temporary loss of control. So there are also some advantages from a security perspective with increased automation. As we move on to the more automated levels, one particular attack is, of course, spoofing or jamming the navigation system, so global positioning system, which means that the vehicle cannot accurately follow its planned route. It might deviate from the path. It might go to paths to places where it's not been intended to go, and moreover, there's also the potential of losing coverage to satellite or RF communications, particularly if you think of an area where there are lots of skyscrapers or in tunnels, which is basically a consideration mostly for urban environments, so the packet delivery scenario mostly. Moreover, you can perform attacks on payloads. For example, if it's an inspection, you can attack the cameras that are mounted to the vehicles and either get the information from there, or if it's used for police survey, you can pretend that there's nothing wrong going on, for example. And moreover, you can maliciously adapt or respond, exploit the responses of automation. So, for example, forcing a return to home function. And as we move yet up in terms of vulnerabilities, at level 4, the UAV is no longer required to be within visual line of sight of the operator. So the operator does not have to keep the UAV in their sight at all time, which obviously means that the operator cannot visually detect changes in behavior of the UAV. So they don't immediately notice if it deviates from the path, which you can do up until the previous level, and respond accordingly. So they purely have to rely on their sensors. And moreover, you can have malicious adaptation again. So, for example, to rely on automation protocols to have a priority landing, for example, by pretending that you have a low battery, for example. And moreover, you could use spoofing to activate its sense and void function, again, forcing it to deviate from a planned route. And sense of void basically means an automatic collision avoidance system. And there you can have ghost vehicles essentially, and then force the vehicle to deviate around them by spoofing an according vehicle. And moreover, you can exploit vulnerabilities in aeronautical communication protocols that exist, for example, ADS-B or AIRBUS, which are legacy technologies. So they're from standardized around 1960s, 1970s, when encryption wasn't the main focus, and that means you can again disturb communication or obtain sensitive data. But on the other hand, the UAV has backup systems. So if there is a vulnerability in, for example, one flight controller, there is still a backup available if they have if they are redundant and not just duplicate. And as we are at the highest level of automation, of course, the classical machine learning attacks play a role, and AI attacks. So, for example, poisoning of training data to change target model boundaries. So, for example, to pretend a particular configuration is not critical. You can gain information about the precise coding if you examine the output of particular test inputs, and you can, of course, exploit vulnerabilities in machine learning algorithms. So, for example, particularly if you use also machine learning to detect any abnormalities, you can then perform the classical attacks that also affect the algorithms themselves. And moreover, you can also extract the machine learning model and thus exploit any vulnerabilities there might be. And moreover, you can also fake input data to trigger a specific system response, also if there is sort of autonomous anomaly detection, autonomous anomaly mitigation, particularly also if you have any cyber defenses on board, which is very familiar to similar systems within non-airborne systems, really. So let's now consider a reference. So what kind of scenarios are we looking at when we perform research in this area? So on the one hand, what's very interesting also from a safety perspective is obviously collision avoidance and path planning. So how can you both take the most efficient route and also avoid obstacles, particularly if they have a higher importance. So for example, in a city, if there is an emergency helicopter planning to land at a hospital roof, you obviously have to detour as any other vehicle. So these kind of considerations, and how do you make sure it's really an emergency helicopter, not just somebody pretending to be, considerations like that. Then how do you deal with emergencies and emergency vehicles? So how do you deal with, for example, low battery power, any sort of bird strike, but so sort of the considerations that also apply to crewed aircraft. But obviously with uncrewed aircraft, there's a control delay, so you cannot immediately respond, which means obviously that the systems themselves have to be much more resilient and much more anticipating of anything that could possibly go wrong and be prepared for emergency situations and things like that. And the third point is formation flight. So when there is more than one vehicle flying closer together than you would normally do, so that means obviously you have to exchange information to make sure you don't crash into another. You have to make sure that you're an optimal distance so you can exploit fuel saving potential, for example. And also you need to exchange a lot of data to make sure that the vehicles are in fact trustworthy, so that they are not going to exploit any data you have on board, they're not going to form a malicious takeover to you, and that they can deal also safely with this formation flight. So for example, that they have a high enough positional accuracy to safely fly away from you and just to remain at a safe distance in this highly safety critical scenario. So let me again provide a bit more explanation on what do we mean with urban air mobility. So as some of you might know, airspace is separated into different airspace classes. And those airspace classes mean that there is both a different level of support provided to the aircraft, so typically from air traffic control, and also that you need to have certain provisions on board if you want to fly in this area. So typically that means that you have a transponder, so an active means to tell air traffic control where you are and the vehicles where you are. And how it's currently envisioned is, or at least for the FAA, so the American Administration for Aviation, is that there are specific corridors where UAVs can take off and land from, and certain altitudes where they can fly at. And obviously that means that you have to ensure that they remain within these areas, which is, again, like I said before, if you can spoof navigation means, for example, that is very critical, because all other air traffic that's flying doesn't expect UAVs outside of this zone. So you really have to make sure that when you design your systems, that they are resilient to those kind of attacks, and that they can either detect those kind of attacks and alert nearby aircraft of this fact, or ideally are not vulnerable to these attacks, or have means to mitigate these attacks. So what does that mean in terms of challenges specifically? When we consider safety, the first point is obviously you need to detect that there are vehicles approaching, which is quite challenging because due to their size, you don't see them on traditional radar. So you have to rely on what they tell you. So in terms of transponders, which of course is also a security challenge, because that means that those transponders have to be accurate and have to be also resilient, and that you have to detect if there are spoofed vehicles or vehicles who don't send anything. The second point is, how do you address vehicles entering a secure zone? So for example, if you imagine the Gatwick incident a few years ago, where Gatwick Airport was closed over a few days before Christmas holidays, really, when there were sightings of UAVs nearby. How do you address that? So how do you address when there's a vehicle that's not in a place where it's supposed to be? Also considering, for example, that it might be a vehicle used to carry blood samples, for example, from a hospital. So, and of course, weight, so you can't, it can drop on the head of an innocent bystander. And the third really big challenge is, what do you do with legacy systems? So what do you do with all systems that are around already, but don't necessarily have have the security capabilities and the safety capabilities to address those challenges? Then the next step is obviously security. We're at the security school here. So particular of interest is secure communication. So in a fixed network, you know which communication partners you accept, and you can just say, okay, I'm not talking to anybody else. But in a dynamic environment such as in a city, you can't really rely on that. So you need to authenticate vehicles, with the added complexity that you don't really have a lot of computational power on those vehicles, and you don't have very powerful computing, because every bit of energy that they consume in all these calculations and handshakes, they have to carry with them, and with that they reduce the distance they can fly. And if you want to fly more distance, you need a larger battery, which makes the vehicle heavier again, and so on and so forth. Then there is obviously the challenge of the secure communication channel, which needs to be post-quantum secure, because typically aircraft, especially larger kind, are in operation for 20 plus years. So it's not like a car that you typically change, I think, every 5 or 6 years. So these will be in operation for a very long time. And moreover, you have to detect spoofing or tampering with the communication channel. As I've said, they are safety critical components, so really affecting flight safety. Then, moreover, as I've discussed in detail, there is a really big impact on security for autonomy. So that means you need to also detect intrusion and prevent them, and also have autonomous decision making, not only for security incidents, but also for safety incidents. So what do you do if you fly into a pigeon, for example? What do you do if there is a gust of wind when you're flying close over a house, for example? And again, how do you secure a lifelong system update process? So how can you ensure that if there's a new security challenge or a new safety challenge, that those systems remain up to date, even if they're sort of in operation by your neighbor, by your child, who don't necessarily check for every flight if there's a sort of a new firmware available for this system. And even if it's even possible to update the firmware easily without assembling everything. And the third one is operations. So the day-to-day operation, really. Here, the most particular challenge is how do you have secure interaction with vehicles you don't necessarily trust? So what do you do if you encounter a vehicle that, for example, uses an outdated encryption mechanism for their communication? You can't just refuse to communicate, because you need to agree how to avoid each other. So there's a big challenge in sort of which data do you share, depending on how trustworthy a vehicle is, both in terms of security, but also in terms of safety. So does the vehicle really know where it is exactly? And the third, which also brings the point of how do you create a network in a dynamic environment, which is very, very similar to the challenges you face with vehicle-to-vehicle communication on the ground, so with connected cars. However, you have a third dimension, which means that there may be buildings in the way, there may be other vehicles in the way, and it's much more dynamic, really. And because you can rely on vehicles to stay on the road usually, but vehicles can move in all, or flying vehicles can move in all dimensions. And the third big point is how can you have a secure information relay over untrusted networks? So that brings me to my take-home messages as well. So both uncrewed and autonomous systems can be very advantageous. They can provide support to humans in dangerous situations, or in situations where it's really inaccessible to do inspections visually. So, for example, in power lines or for bridges. But these aspects of autonomy and collaboration can also be exploited. However, they can also be protections from certain attacks, but again, bringing different challenges as you increase automation. So what I'm really trying to say is that different automation levels bring different risks, but also different opportunities. And of course, finally, drones are maybes. And with that, I'd like to conclude my talk and our talk, and we're open for questions. Thank you very much.
very good. Thank you very much for the great presentations, and it also worked out very well here, so very good. So I would have a first question, and then I'm sure that we have lots of additional questions in the room and also in the Slido. So both of you talked about, in some way, opportunistic sensing and also opportunistic operation of the entities you were talking about, so of the cars, and also about the UAVs. How can you trust in the data when you have such distributed entities?
I'm afraid I only got the second half of your sentence because the audio was interrupted.
So, yeah, I say it again, is it working okay?
Yes, now it's
Okay.
fine.
So both of you talked about opportunistic sensing and operation of the entities you were talking about, so of the cars and of the UAVs, because they are not operated by someone trusted professional, but they're operated by me, for instance, or they're even flying on their own. And my question is, how can you trust in the data that those entities send? So is that an issue, and how can you improve the trust? So this is a question.
Yes. This is actually a line of research that we're investigating in one of the European projects we're performing at the moment within the Concordia project, together with the University of Insubria. So, which kind of parameters can you use to determine if a vehicle is trustworthy? How can you establish that in flight? So which pairs are most suitable to detect, which are most available. So this is indeed a very interesting line of research which we're performing at the moment.
And just perhaps to complete this answer, I think that in the automotive world, it's a little simpler than the UAV's word, also because the car have, let's say, a whole process that was well established also before, in order to manage the car keys, and they have already some crypto elements in their equipment, who is trying to can you hear me? Okay, I was just saying that in the car industry, in the automotive industry, there is already some, let's say, history around the authentication of the cars using some crypto element in the production chain of the car manufacturer, and therefore they are still using this in the logic of the connected car in order to connect the car to the overall industry. And there is some European regulation about that on the standards that the car manufacturer have to use to authenticate the communication of their car to the infrastructure.
Maybe 2-3 questions from Slido that asked by the audiences. This can be an interesting one. Who is liable for when an incident happens?
Sorry, I didn't hear the question. Oh.
I guess our legal departments would be the right people to answer that question. I have no idea, I'm afraid.
Yeah, for the automotive challenges, it's a point that is already addressed at the European Commission level, where there is some legal discussion around the table for that.
Okay. The next is there standardization for security of cars and UAVs? If yes, who carries it?
So to start with the cars, which is more my area, I will let Cora answer for the UAVs. For the cars, there is standards. There is some standards that are handled by the IEEE, and there is also standards that are at least technical specification that are published by the ETSI organism, especially on the, let's say, the telecommunication part.
And for UAVs, there are specifications typically developed by the airworthiness authorities. So EASA in Europe and the FAA in the US. However, at the moment, there isn't really a lot in terms of cybersecurity. There is regulation anticipated for that, but it's not really public, or it's still under development at the moment. And there are also standardization bodies. So ED 202 is, for example, a regulation that also affects cybersecurity. So EUROCAE.
Any questions from the audience? Then maybe let me pick one last one from the Slido, and that can be, how is the collaboration between competitors regarding cars and UAVs?
You
So
mean
what I
the
can
competition? That's it?
Say that again. So shall I repeat the question or?
Yeah, please.
Yeah. The
Thanks.
question is asks how is the collaboration between the competitor firms? Like, to what regard do you collaborate in terms of for cars and UAVs?
For the car industry, let's say that there is some consortium, for example, the car-to-car consortium, that are conglomerate of car manufacturer. They, let's say, all know that their interest is to go to the connected car, which is the first step for the autonomous one. So there is not really competition on the, let's say, on the standards and how to implement the interface. The competition is more on the services that they would like to offer. But let's say that on this specific part, competition is not an issue as far as they will rely on more standard interface. The competition on the standards is more at the, let's say, the car manufacturer providers than on the car manufacturer itself. And as far as the car manufacturer are able, let's say, to agree on the best solutions in order to set up the main standards, then the provider have to apply that. So there is not, let's say, critical competition on the interconnection part.
Yeah, for UAVs or for aviation in general, it's very similar. So usually you work together in there are specific working groups at the various rulemaking authorities. So both on an international level and also on European or American level. And there it's really more it's more technological discussion than really
competition, or it's really more of finding a way of solving the challenges, and it's not really a competition as such.
Thank you. Thank you for answering the questions.
So maybe Cora, to you, I would have maybe a last question, which is security is also about safety. And when you think about UAVs, I'm thinking about maybe less traffic, but much more variation in the entities that are flying around. Is that a big issue for securing UAVs and their operation?
Short answer, yes.
Good. All right, then I will just turn you around so that you also get an impression of the room. And okay, so here's the audience, and and thank you also from my side. It was a great presentation, and now the warm applause is yours. Thank you very much.
Thanks a lot.
Great. Yeah, so thanks a lot. And
Thanks for having me.
all right, have a great day. See you.
Bye.